is passing through the tube. The hydrogen unites with the oxygen of the rust to form water, which collects at the end of the tube. The iron oxide, having lost its oxygen, has become iron, for now the magnet attracts it. This is obviously a process of oxidation and reduction. The hydrogen uniting with the oxygen of the iron oxide is oxidized to water. The iron oxide, by losing its oxygen, is reduced to iron. Hydrogen is the reducing agent. Coke is another reducing agent. Here we see it loaded into cars and hoisted to the top of a blast furnace to aid in reducing iron ore to iron. Coke is mainly carbon. Iron ore is composed chiefly of oxides of iron. In this cross-section drawing, we see the furnace being filled with alternate layers, one of ore and limestone, and another of coke. A hot blast rushing up from the bottom of the furnace converts the coke into the gas carbon monoxide. This removes the oxygen from the iron ore, reducing it to metallic iron. The continued intense heat melts the iron, which passes through to the bottom of the furnace and is drained off. Still another reducing agent is magnesium. Here is a metal which burns in air and liberates more energy in the form of heat than any substance considered thus far. The resulting white substance is magnesium oxide. Steam is being generated in this flask. I ignite a magnesium ribbon in the water vapor inside. In this reaction, the magnesium extracts oxygen from the steam and liberates hydrogen, which we see delivered at the left. The magnesium, reacting with the water, becomes magnesium oxide and liberates hydrogen. With this magnesium powder and this block of dry ice, I shall demonstrate in even more striking fashion the reducing power of magnesium. Dry ice is carbon dioxide, ordinarily a gas, but here so cold that it is a solid. In it I have made a hole in which I have placed the magnesium powder mixed with pulverized dry ice. The magnesium powder within the mixture itself burns furiously in spite of the extremely low temperature by taking the oxygen from the powdered dry ice. This is reduced to black bits of carbon. The reducing power of aluminum is shown in the welding of a steel rail by the Goldschmidt process. A mixture of aluminum powder and iron oxide is poured into a crucible and primed with ignition powder. A mold is formed about the rail, and the crucible is mounted in place on top of the mold. The reaction is started. The aluminum, in reacting with the iron oxide in the crucible, reduces it and generates enough heat to melt the resulting iron. The crucible is tapped. The iron runs down into the mold, welding together the two ends of the rail. Oxidation and reduction are always going on in our surroundings. They are occurring in the burning of fuels, in the smelting of metals, and in the rusting or corrosion, while that which glass rubbed with silk is positive electrification. Evidently, unlike kinds attract each other, whereas like kinds repel. We can interpret what we have just seen by the hypothesis that all matter is composed of both positive and negative electricity in equal amounts. When the amber was rubbed with fur, the amber acquired an excess of negative electricity and the fur an excess of positive. The glass, when rubbed with silk, was left with an excess of positive and the silk with an excess of negative. On certain substances, such as glass and amber, Electrical charges accumulated in this manner remain localized. These substances are called insulators. In other substances, notably the metals, negative electricity under certain circumstances moves about. These substances are called conductors. Note that the charges concentrate at the pointed end. Only an insulated metallic conductor may be charged. As soon as this insulated metallic object, which has been charged negatively, is grounded by the conducting wire, the excess negative charges pass off into the ground and are lost, nor can it be charged positively, because any positive charge conferred upon it is immediately neutralized by negative charges attracted thereto from the ground. Note that only the negative charge moves in metallic conductors. Electrical charges may be detected and their kind determined by the gold leaf electroscope. When the leaves are charged either positively or negatively by contact of a charged body with the knob, the leaves diverge because they are repelled by the identical charges on them. But even if the charged body merely approaches without touching the uncharged knob, the leaves move apart. How can this happen? Recall that electrification of one kind repels charges of the same kind. Hence, as a negative charge is brought near, negative charges in the material of the electroscope are repelled downward to the leaves, resulting in an excess of negative charge on the leaves, which causes them to diverge. When we ground the electroscope while the charged body is near, the excess negative charges through their mutual repulsion flow down to the ground. Upon breaking the ground and removing the charged body, the leaves will be found to diverge and to be positively charged. This is called charging by induction. This electroscope is positively charged. Let us use it to determine the kind of electric charge on this object. When it is brought near the knob, the leaves diverge still more. This shows that the leaves must have acquired additional positive charges by the loss of negative charges which have been drawn away from them toward the knob by the unknown charge. Therefore, the unknown charge must be positive, since negative charges have been attracted. Suppose, however, the approach of a charged body causes the leaves of the electroscope to collapse. Remember that it was positively charged. We conclude that negative charges have been forced down to the leaves, neutralizing some of their excess positive charges. Since negative repels negative, the unknown charge in this case must have been negative. In this fashion, the electroscope may not only indicate kind of electric charge, but roughly measure its quantity. However, the myriad uses of electricity in modern life involve the necessity of exact measurement. The quantitative measurement of electrical charges is made by means of this instrument called the electrometer. The principle of the electrometer is the same as that of the electroscope. The essential parts of the electrometer are these: a needle